we're on this. Okay, and I'm gonna throw my image over here with all the people. There we go. Didn't have everybody come back, but we've got a group. Okay, so what we're going to look at here is we want to look at these exact same 3 steps, but the reagents change, okay? So the 3 steps in the mechanism are always the same. We just have to make sure we create that electrophile at the beginning of the reaction. We're going to see that in our reagents. Some of them are going to look similar, but when we did a reaction with an alkene, we could add bromine to it, and that would react by adding across that double bond, okay? That didn't work with aromatic rings. That's why they thought, oh, it's somehow different. So we have to find a way to make it work, okay? So let's look at some different ways on doing these reactions, okay? So in the case of aromatic rings, we can add halogens across them. We can do substitution reactions with halogens. However, we must use a catalyst, okay? And in this case, we're using a catalyst called FeCl4, okay? The reason we're using this is we're gonna generate a positively charged chlorine in the process. And so that's what we're gonna look for, creating that electrophile. And then when we end up doing the substitution reaction, the half of the chlorine from the chlorine gas goes to the ring, half of it goes with the hydrogen away to make HCl, and we regenerate our FeCl3 catalyst. Notice that FeCl3 is the same as the chlorine. If we were to use bromine, we have to use FeBr3, because otherwise you'd get those halogens possibly mixing together. So you'll see that that iron catalyst for chlorine is going to be chlorine, and for bromine it's going to be iron bromide, okay? So that's what I want you to pay attention to that. Now, we can add other things to this ring as long as we're creating a positive charge. In the case of something like nitric acid here, so nitric acid itself will not react with that unless we add another strong acid to it to generate some kind of positively charged nitrogen species. And so we need to look for where that nitrogen is positively charged. Okay, so when we're doing with the bromine or the chlorine, we have to react it with something that is that ferric chloride, in this case, FeCl3. In this case, our ferric chloride is acting as our Lewis acid, meaning it will accept electrons, okay? And in this case, our chlorine is acting as the Lewis base, because look at those lone pairs on those chlorines, okay? Now, that chlorine-chlorine bond, because we have 2 electronegative atoms, is a nonpolar bond. So the proximity of that Lewis acid, that ferric chloride, creates the polarized bond and therefore creates our electrophile. So the first step is our electrons, of course, going and interacting with the iron. It's accepting the electrons from the chlorine. When it does that, that changes the formal oxidation state of chlorine to this +1 right here. And so to take it down to a regular neutral chlorine, it takes the electrons away from the previous chlorine, giving us our chlorine plus, and this entire compound is the counterbalancing anion, okay? So we create this charged ion pair, okay? Of this charged ion pair, the iron tetrachloride anion is our nucleophile, right? But we have our chlorine plus is now our new electrophile, our positive charge that the benzene can reach out and grab now. So our next step, of course, is one of the double bonds of the benzene ring is going to reach out and form a new sigma bond, and we break aromaticity when we do it, okay? That positive charge is going to resonance stabilize moving around that ring. And that's important for when we look at adding something else to the system. We're going to see that positive charge moving around that ring is going to control where other things add, and it'll control our rate at things. So remember that we have this resonance stabilized group. of resonance structures where that positive charge is moving around the ring. And of course, our last step is to lose a proton. Get those electrons back into the aromatic ring, okay? So to do that, our former Lewis acid, once we formed that chloride, is now has a negative charge. And our former Lewis acid with that complex now acts as our base. So when we have that come in and act as a base, the electrons kick into the ring, we generate our double bond, so we re-aromatize our ring, okay? Now that Lewis base decomposes to give us our HCl as a byproduct and regenerates our Lewis acid catalyst, okay? So we call it a catalyst because we only need a little bit in there to get it to continue to go through the process. And we have it in there as also acting as our Lewis base to help remove the proton from the benzene ring. So same three steps. We form a positively charged species. The benzene reacts with the positively charged species to generate a resonance stabilized compound, and then it loses hydrogen to some Lewis base in the system, okay? So let's see how that applies to nitration, okay? So we had to somehow form a positive charge on nitrogen because that's where we're gonna make that new benzene nitrogen bond, okay? So that being said, we are going to take our nitric acid here and we're going to protonate it to make us have a good leaving group here. So now that it's protonated, we have an acid that is being protonated by a stronger acid to generate a good leaving group. When this leaves, it leaves as water, a neutral species. So if we do decompose this product here, what we're going to see is it's going to make water plus our electrophile, our positively charged species. Now, if we go back and do our formal charge and look at our Lewis dot structure here, the positive charge is on nitrogen. And we'll know this to be true because the product we get is going to be benzene bonded to the nitrogen. So you might want to just kind of go through the book and look at that and make sure that that's happening, but you should prove to yourself that the positive charge is on nitrogen, okay? So that being said, anytime we create a species with a positive charge, that's going to create our new sigma bond between the material we are adding to it, and we're breaking that sigma bond with the hydrogen. So that's why it's a substitution reaction. So, and whatever that new bond is where the positive charge was in the reaction, okay? So that being said, we can do that with sulfuric acid. The same thing happens. Another molecule of sulfuric acid protonates the sulfuric acid, giving us an SO3 positive charge as our reactive species. In the presence of HRX, we can actually take an alkyl group with a halogen on it and have it form that same complex, giving us a carbocation, a stabilized carbocation, and that means that carbon is the one that ends up on the benzene ring. And then we have a new reaction, which we haven't done before, which we call an acylation, okay? And in an acylation, we're creating the positive charge on a carbonyl carbon, okay? So when we generate that positive charge on that carbonyl carbon, that carbonyl is the part that's going to attach to the benzene ring and generate our hydrogen. And in this case, it's usually whatever this is here creates the hydrogen goes with that as the base, okay? So, but the first step, actually the mechanism in all of these reactions is exactly the same. Generation of a positive charge, attack by the benzene to the positive charge, and then kicking out of a hydrogen. Okay, so let's talk a little bit more about the acylation right here, because it's a little different. It's forming that carbocation is different than other things we've done so far. Okay, so I want to specifically talk about that. And so the idea here is that our acid chloride or acyl chloride is actually a derivative of carboxylic acid. where we take the OH away and add a different electronegative atom, in this case, chlorine, okay? So that being said, we have a carbonyl with a polarized bond with that chlorine. Chlorine likes to leave as a negative charge, right? That's one of our leaving groups here. That means it's going to generate a positive charge on this carbonyl compound right here. When we have that positive charge on that carbonyl, it's the part that's going to be attacked by the benzene ring electrons, and then it's going to kick out hydrogen from the other half of that double bond to generate our HCl and our new carbon-carbon bond here, okay? So this looks to be a really different reaction, but it follows the exact same mechanism as everything else. The only difference is in this one, we're using a different Lewis acid here. Instead of iron trichloride in the chlorination reaction, we're using aluminum trichloride as our Lewis acid to generate our intermediate species, which would be the aluminum tetrachloride anion and our carbocation on this carbonyl compound here. Okay, so let's see, do we have that? Yeah, here we go. So the first thing that has to happen is we're going to use our Lewis acid to pull away the chlorine to give us our electrons to be able to kick in and generate our carbocation right here. Okay, so basically the first thing that happens is our Lewis base is accepting electrons, giving us these two bonds to chlorine and a positive charge on chlorine. Remember, chlorine's electronegative. It would rather have its electrons than not. Therefore, these electrons will kick in, generating our carbocation and our new Lewis base that we're going to use at the end in step 3, okay? Let's see, that should be the next one. Okay, so let's go step by step again, proving to ourselves what's going to, whoa, wait. That's one step too far. Let's see if I can get it to go this way. There we go. Yeah, okay. So this is the first step when we're doing a acylation, which is the ACYL, because we have that carbonyl carbon as the carbocation. We don't have to have a carbonyl to generate that. And when we do that, we call that an alkylation, a Friedel-Crafts alkylation, okay? So it follows the same mechanism, except we use our Lewis base, our aluminum trichloride here, to generate a carbocation on the alkyl group. That's a carbon without the carbonyl. So we can generate the same kind of species to gives us the carbocation, our stabilized carbocation, and then it will react with the benzene ring again. Again, the formation of that cation is the first step. Okay, so in the case of an alkylation, we have our aluminum chloride come in as our Lewis acid. We have the generation of our new chlorine aluminum bond and our R chlorine bond, but then again we have that negative charge on chlorine. So it takes the electrons away, yielding our carbocation right here as our electrophile. Note, because this is not a resonance stable carbocation, it will rearrange if necessary. So we need to pay attention to if it was a primary alkyl halide, does it rearrange? If it's a secondary alkyl halide, does it rearrange? Remember, our tertiary carbocation on our carbon chains is the most stable. Okay, so again, the first step is to generate our carbocation. Our carbocation can rearrange before actually doing step 2. So we're going to look at that in a minute. But of course, what happens is our benzene ring reacts with our carbocation as our nucleophile. Then again, we get this resonance stabilized intermediate here. Then our aluminum tetrachloride acts as our Lewis base, regenerating our Lewis acid plus HCl, and we now have a new carbon-carbon bond. Okay, so that being said, they will rearrange to give us, okay, FC up here stands for Friedel-Crafts alkylations. They only work really well when you have a secondary or tertiary carbocation. If it can rearrange to form a secondary carbocation, it will rearrange to form a secondary carbocation. Okay, the other thing about a Friedel-Crafts alkylation is that certain groups inhibit the reaction. Okay, so if you have anything that is an electron-withdrawing group, or you want, the easiest way to think about that is anything with a partially positive or a positive charge. All of these carbonyls are partially positive. We'll learn about that in a couple chapters. Anytime you have a positive charge or a partially positive charge here, it inhibits the reaction. Okay. Now that same concept will lead us into direction on where reactions happen on the rings, and we'll talk about that in goal number 3. Okay, so because the first step in those Friedel-Crafts alkylations is the generation of a carbocation, that means that we can actually generate those carbocations with any Lewis base. We can generate that by protonating, like in this case here, we're going to end up using a strong acid here. What it's going to do is it's going to add a proton to here, giving us our partially positive charge here, because these electrons are going to come out here to grab onto a hydrogen, generating our carbocation. So remember that first step in the addition of HCl across a double bond or something like that is the generation of that carbocation. Same thing happens in these strong acids right here. But notice that the other part of that acid is not a good nucleophile, okay? So we're using hydrogen, like this one would be, if we use this phosphoric acid here, we're gonna generate O4 as minus. It's not a very good nucleophile, so instead of adding to the other side like an HCl would, we actually have that carbocation sit around long enough that the benzene attacks it as our nucleophile. So that's why we're going to see these acid catalyzed alkylations happen with things like sulfuric and phosphoric acid, but you cannot do it in the presence of HCl or HBr because that's just going to add across the double bond. So when you see these acids in benzene, start thinking about that alkylation reaction. Okay, questions on the mechanism of these electrophilic additions to our double bonds here. Okay, Zoom chat's open. I think everybody's still there. I haven't frozen yet. Okay, while you're adding your questions there, again, the key is it's those same 3 steps every single time. You just got to figure out how to generate the positive charge and which atom the positive charge is on. And then where it ends up connecting on the benzene ring is very easy because that's where the positive charge was. All right, I'm going to stop this one and move to goal 3. Okay. In goal 3, we're going to talk about ring directors. Now, in the previous reactions where I was talking about the different reagents to look for in the mechanisms, okay, one of the key things here is that that 3 different resonance structures that stabilize that positive charge on the ring, okay? Where those positive charges end up tells us that whether or not it's really stable or not stable, okay? So now we need to think about where is that positive charge, and is there something already on the ring that's going to help that positive charge or hurt that positive charge? That's the whole point of ring directors, is things that are partially positive or have a positive charge are going to not make that positive charge happen on that same carbon, and things that actually can help stabilize that positive charge will actually direct things to different things. So that's the key here, is that positive charge going around the ring whether or not the group already attached to the ring is going to help that positive charge or hurt that positive charge. Okay? So let's see, we are still doing okay on time. I should get all the way through this one, and then we can actually do some problems. Okay, so if we just had benzene itself, all of these reagents we just talked about will react about the same because there's nothing else on the ring. It'll form that positive charge will move around the ring, and then eventually it kicks out a proton to give us our final product, okay? However, as we learned from the video, there's a bunch of different alkyl groups possible here, or attachments possible on benzene, and that changes their name. But the other thing they have is they have different electron donating or electron withdrawing properties. Sorry. So in the case of these species here, we can look at whether or not the substituent has electrons on it or is electron withdrawing. So if we think about this one right here, phenol, we know that there's 2 lone pairs on that oxygen here. This nitrogen has a lone pair. These carbons, remember, carbon-carbon bond is not very polar. So it's not pulling electrons away. It's not donating a whole bunch of electrons, okay? These have lone pairs on them, so they can probably donate, which would help a positive charge. What we're going to learn is that these are partially positive carbons. And whenever we have these partially positive substrates here, that's going to hurt where that positive charge is. So that's going to change, influence it, or direct it to a different location. Now, if we look at this one, this ether at the end here, we have a total of 2 lone pairs right here. So that's probably going to help a positive charge because it has electrons to donate. Okay, so whenever we have a benzene ring hooked to another benzene ring, we typically call that substituent a phenyl group, and it is considered electron rich, okay, because of those double bonds here, okay? Now, once we put more than one thing on there, we now have isomers, okay? The first thing we need to know about these isomers is the different locations, okay? So if they're next to each other, like I had a methyl group here and a methyl group there, that's what we call the 1,2 isomer because they're on carbons next to each other. And that's called an ortho, okay? It's just another name for 1,2 substitution, and it's ortho. 1,3 is meta right here. And then the 1,4 is para, okay? It's important to know ortho, meta, para, because when we talk about direction, we tend to call them ortho-para directors or meta directors, okay? So you can direct it ortho and para at the same time, or meta. Those are the only 2 possibilities. So knowing the ortho, meta, para is important to know which way it's directing, okay? So these reactions change their rate and orientation based on whether or not the group helps that positive charge or hurts that positive charge. And so anything that has a partially positive charge or positive charge is deactivating toward further substitution or slows the reaction down, okay? So orientation is where it goes, rate is how fast it goes, right? Ortho-para directors tend to be, most of the time, except for one case, they are promoting the reaction and therefore speeds up the rate. Meta directors all slow down the rate, okay? So that's a key thing we need to look at here, okay? So let's look at some of those and figure out kind of what the contributing factors are and what the generality between the different directors are so that we can notice them. Even if we've never played that functional group before, we can see something about it that tells us yes or no, okay? So the first thing I want to look at is our group here that we're going to call ortho-para directors. What that means is that, of course, we're going to promote reactions that are 1 carbon over from the substituent or 3 carbons over from the substituent. So if our substituent is here, it's going to direct in this position or that position, because this would be the 1, 2, which is ortho. This is 1, 4, which is para. Okay, so that's what our ortho and para directors are. And so basically, if you had an OH here, and we reacted it with bromine and ferric bromide, we would have the reaction where it's going to try to go, a bromine is going to go ortho, and a bromine can go to the para. That's what ortho-para direction means. Okay, so so it's not about the reagent being used, it's about what group is already on the benzene ring. That's what you need to pay attention to. So if the group is already on the benzene ring and it seems to have a lone pair on it, that's going to be an ortho-para director. Notice that right here, these are strongly activating. All of these in the strongly activating group have at least one lone pair on the atom directly attached to the benzene ring. That is the feature of a strongly activating ortho-para director. Okay. Notice the next set of moderate activators here. They all have an atom with a lone pair on it. However, they also have a carbonyl attached to that same atom. What that means is that the carbonyl is partially positive, and therefore not all of the electron density can be donated to the ring. Some of it's being donated to the carbonyl compound, the CO double bond compound. So the lone pair is activating, but in this case, the lone pair is not 100% shared. The next thing we have here is what we call weakly activating. And they're weakly activating because the carbon-carbon bond is not very polar, and therefore it's not really adding electron density, but it's not taking electron density away either. Okay, so that's what we call our weakly activating. And so all of these, if they're already on the ring, are going to promote ortho-para direction. Okay. And if the, okay. Now, the last thing we have are ortho-para directors, but we call them weakly deactivating. Okay. What that means is there's two different effects happening here. We have lone pairs that can donate. Okay. So that's the ortho-para directing part. However, they're all electronegative atoms, meaning they're all trying to pull some of that electron density back. So the lone pairs are actually overlapping with the pi cloud to direct it ortho-para. However, the electronegativity is pulling some of the electron density away. They're still ortho-para directors, but they're not what we would call strongly activating. They are weakly deactivating. Okay, so that's the similarities among all the ortho-para directors. Now let's look at the deactivators, and all the deactivators, all the meta directors are deactivating, okay? And they all share the same feature, that if we look at the atom directly bonded to the benzene ring, all of them have a partially positive or a positive charge, okay? So if we think about our carbonyl, we'll learn that this side of the carbonyl is partially negative because of the lone pair on the oxygen. This is the part that's going to be partially positive. Here, I do not want to, let me erase those. I don't want to accidentally. And so anytime we have a carbonyl bonded directly, it has a partially positive charge on that carbonyl, meaning it's always going to deactivate. And when it deactivates, it also meta directs, okay? The other thing we have are what we call strong deactivators. And if we did the formal charge on nitrogen here, it's +1. This has a +1 on nitrogen as well. And notice these right here are carbons, which up here we're weakly activating, but they have 3 electron withdrawing groups. And the lone pairs can't like up here, they can actually kind of back donate. They can donate through the pi cloud. They're far enough away they can't. So these are partially positive as well. And we call those strongly deactivators. So anytime you see a partially positive or positive charge on a substituent on a benzene ring, it is always deactivating, and they're always meta-directing, okay? Everything that has a lone pair on it can be a ortho-para-director. However, if they're halogens, because of their electronegativity, they're slightly deactivating, but they're still an ortho-para-director. Okay, so does everybody see that those two features, lone pairs available, makes them ortho-para-directing? Having a partially positive or positive charge makes you meta-directing. Okay, that is the overlying theme with all of those structures. And so even if you don't recognize a functional group, you should be able to look at your Lewis dot structure and say, ooh, this is partially positive, or this has lone pairs. And you can get a really good guess most of the time. Okay, all right. Group chat, all right, still there. Okay, so the reason ortho-para-directors work is that it is the ortho-para attack creates the more stable cation than the meta attack, okay? And the reason meta-directors work is the meta attack forms the more stable carbocation, the three resonance structures, than with an ortho-para attack. So let's look at that in a little more detail. So in this case here, we have this OCH3 group, which means it has two lone pairs. So just immediately saying two lone pairs, it's going to be an activator, and it's going to be an ortho-para-director. Okay, let's figure out why. Let's attack meta and look at the stability of the carbocations formed, okay? So if we attack meta right here, and so that we form our first bond that is 1, 2, 3, the third carbon over. So 1, 3 is meta. Okay, we're going to form a carbocation that's near this oxygen with a lone pair on it. And we're going to create a carbocation that's near that oxygen with the lone pair on it. And we're going to create a carbocation opposite the one with the lone pair. Okay, the lone pair on that activator never gets used to help stabilize that partially positive charge, or that positive charge on the benzene ring. Therefore, we only have 3 resonance contributors for our 1, 3 meta attack. Okay, now let's assume instead of doing a meta attack, let's look at a para attack, because para attack and ortho attack will give us this carbocations in the exact same places. Okay, so if we do that exact same thing and the electrons come out and grab our nitrogen, we're going to generate a partially positive charge next to that, a positive charge next to that, which is resonance stabilized with this positive charge, which if we went the other direction, we would have that positive charge here, okay? Notice we have a 4th resonance contributor we did not have before. In the case of having this positive charge wind up on the same carbon with our donating group, we can actually now use the lone pair from the donating group to contribute to that and have a positive charge outside the ring, okay? In meta, we only had 3 resonance contributors. Because of we did the attack at the para position, we have a 4th resonance contributor. What that means is if we have a 4th place to put that positive charge, it's more stable. Therefore, it is going to be the preferred energy, okay? So in the meta attack, we only had 3 resonance contributors. In this para attack, we have 4 resonance contributors. Therefore, para attack is favored with these activating systems. And it has everything to do with having these alone pairs be able to donate back into the system, okay? So you can draw this kind of resonance stabilized cation for all of your ortho-para directors and activators by having those electrons come in and contribute to a fourth resonance stabilized positive charge. Okay, so now let's go to why a nitro group might be a meta director. Okay, so this is kind of working in the opposite direction. Here we are going to form the first, if we do a meta direction here, we're going to form our carbocations, and they're going to be in that same 3 positions you had before. And so you end up with 3 resonance contributors to our system, okay? So that's no different than if we had that nitro attack on that other donating group, okay? But what if we attacked instead at that meta, what if we attacked at para? What we have now is that our carbocations are going to move around to here, here, and here. The ones here and here have the same stability as the carbocations from the previous contributors. However, this one is next to our partially positive substituent. So now you have a partially positive substituent and a positive carbocation. Now they're going to repel each other. Because that works out, that makes this a disfavored resonance contributor, meaning we only have 2 resonance contributors now. 2 resonance contributors is less stable than 3 resonance contributors that we find in our meta attack. Okay, so that fact that we have that partially positive group on there, number 1, deactivates the ring a little bit because of that partially positive charge. Number 2, because of the formation of 3 resonance stabilized resonance structures in the meta attack, it's favored over the one that only forms 2, and therefore it is deactivating because of the positive charge, but it's meta directing because of the greater number of resonance stabilized intermediates. Okay, so what that tells us is that anytime we have something with a lone pair, that means it's going to help delocalize that positive charge, and therefore it's going to activate it by that having those lone pairs be able to contribute to that extra carbocation intermediate. Anytime we have these partially positive substrates, inductively it decreases the electron density in the ring and therefore deactivates it as well. All right, questions on that? Okay. So the last thing we have is halogens, okay? Inductively, because they're electron-withdrawing groups, they want to deactivate the ring slightly. However, because they have lone pairs, they are ortho-para directors. Okay, so it's kind of a 2 different effects there, which is why they're ortho-para directors because of the lone pair. However, because they're electron-withdrawing, they are trying to be deactivators. Okay, so that being said, we can use this to our advantage. Okay, the way we can use this to our advantage is by helping us know which reagent's going to go where to figure out which reaction we need to do in which order. So for example, if we had this right here, toluene, which is the methyl benzene, okay, the methyl group is ortho-para director, slightly activating. It has no lone pairs to donate, but it doesn't have a positive charge, so it's slightly activating ortho-para director. Okay. Now, if we wanted a specific isomer of a compound, we would have to change the order in which we did the reaction based on whether or not we wanted it as a para functionality, in the case of this first one here, or an ortho functionality. Because right here, as it sits, toluene is an ortho-para director, which means if you wanted the nitro group in the para position, You want this methyl group to be intact because it's going to be a donator. It's going to give you the substrate that is going to have the para direction or the para isomer here. And then when you oxidize down that methyl group, you're going to end up creating, this is electron withdrawing group. It's a carbonyl, carboxylic acid here. It's got that carbonyl on it, which is partially positive, meaning that it would deactivate the ring or direct it meta. So let's do it the opposite direction around. Let's, instead of using this as our para director, let's oxidize it down first. Now it's, number one, deactivated, so it's going to be harder to nitrate. Okay, so that's going to make this reaction a little harder. However, because this is a deactivator and a partially positive charge, it's going to direct it meta. So this is the only product we'll form if we did the reaction in this order. And this will be the only product we form if we did the reaction in the other order. Okay, so paying attention to your orthopara directors helps you decide which reaction to do first. All right, questions on that? Okay, I'm going to stop sharing right here. Okay, so that gives us about 5 minutes to ask additional questions. Okay, now again, this is in everything in the chapter. The videos have all the other kind of details about reagents and stuff. What I wanted you to see in number 1 is that how you identify aromaticity, even though it may not look like a benzene ring. In number 2, I wanted you to see that the 3 steps in the mechanism are always the same. Generation of a positive charge, attack by the benzene to the positive charge, and then elimination of a proton, okay? And in the case of using a catalyst, you regenerate that catalyst at the end. And it's typically a Lewis acid catalyst because it accepts electrons to form a positive charge on something. In number 3, I wanted you to see the similarities between ortho and para directors having electron density or lone pairs, and that meta directors have a partially positive or positive charge. And ortho para directors tend to be activators, meta directors tend to be deactivators. Okay. Questions on the goals for chapter 9? Okay, I'm going to stop recording so you can ask your questions without being recorded here. Let's see, stop recording.